I don't think I get a 3, 2, 1 count on here, but that's fine. So this is just a quick video to run you through the code that we've done in R for the entirety of this quarter. All of the data that will be used in this video you guys should have access to. It's literally just copied and pasted from everything that we've done in class into one R script. So let's get started with that. So starting off, we're going to do the correlation. So I have imported my data as a CSV file. I will be giving you guys an Excel file with all of the data all in the same sheet. So be very careful about how you name your variables to keep everything in order. But just to get through doing it, I'm going to run this line of code which brings in my data and it renames it or nicknames it into vamp data. So you see it pop up over here. The next thing I will do is run a correlation test which uses vamp data, the variable I just created, $, and then the two variables that I want. So I'm going to run this, and just real quick, you may notice that there's this indentation here. That is for ease of reading for you guys, just because you won't be able to see the entire line of code, and if there's some stuff over here, I don't want to have to constantly scroll over. So it runs the exact same way. I can just hit enter or return and it'll do it like that as long as it's within the same parentheses or brackets. It'll read it all as one line of code. So right down here we have our p-value, a super significant p-value, and a very strong correlation. So obviously these two variables are strongly related, so number of blood donors and number of vampire sightings. This is, once again, data from class, and it's also included with the confidence interval. So moving on, t-test and effect size. It's important that you guys do both of these now that you know how to for your test. So the library effect size is pretty much the only library we'll need. Installing packages, once you do it the first time, you may not need to do it again, but if you run library and you get an error, you probably will need to run the install package again. So I'm going to have those hashtagged out. Oh darn, that's a 3. I'm going to have those hashtagged out, and if necessary, you can just erase the hashtags and run the install packages. But you will definitely need to run the libraries to make sure that you can do what you need to do. So for this one, I have my paired data and my independent data for the t-tests. And for the test, you guys will need to know the difference between the two, just from reading the context of the question. So this is the code for the independent two-group t-test. I'm comparing male mean scores to female mean scores. Pretty sure I can click this. Yeah, it's like scores on something, just data that we created. So I run my t-test and I get this super significant p-value, and now I can run my Cohen's d for the effect size, and I get a large effect. The negative basically just means that female was larger than male. If it was positive, then male would be larger than female. That's just one way to look at it. The mean difference, that group, is bigger than the first group. That's why the number is negative. You can look at the means up here. So mean of X, which is the males, was 53. Mean of Y is 64, so Y was females. Y is bigger than X. That's why you have negatives. Sorry if I'm confusing you guys, but feel free to pause, rewind. I'm uploading this to YouTube so you can watch it at double speed. But moving on, t-test for paired, I did t-data p, count time 1 versus count time 2, and paired equals true. So that's telling R that this is a paired samples t-test rather than an independent samples t-test. That's pretty much the only difference between these two lines of code of line 30 and line 37. So I'm going to run this. Did it run? That's Cohen's D. Let's try that again. Gonna run this. There we go. So we have our paired t-test, and this one is not significant, so I do not need to run a Cohen's D for it. However, just to show you guys the code for it, you have these three things being written out and true, as opposed to just the empty Cohen's D of the two variables for the independent samples t-test. And as you're typing things, R is pretty good about telling you what things are. If you start typing them and then highlight them, it literally tells you logical, indicating whether NA, so not applicable, so empty data, essentially, should be removed before computation. So if there was less data in time 1 than in time 2, what to do with it. So you're telling it with this command to remove it, true. Pooled is your variance if you want pooled or unpooled variance, and then paired is once again telling R that it's a Cohen's D for a paired sample t-test. Also, real quick, just for you guys' testing reasons, I would recommend when you are writing your code, after you've imported your data, whenever you are typing in your variables in your data frames, let R autofill it for you. And that way you can get it exactly the way that you need, rather than having to worry about a missed capitalization or, you know, the whatever these are called for your data, making your things not appear. So autofill is your friend. This has been a public service announcement. Moving on, ANOVA. I know a lot of people had difficulties with the car, which was for the Levine's test. Honestly, for the test, if you can get it to run, that's wonderful. If you can't get it to run, that's fine too. I'm not going to take off points, but show me that it does not run. So when you're running your library, if the error pops up for car, whoa, it just moved. If the error pops up for car that loading failed, that's fine. I'm not going to take off points for you there. mdata is what I'm calling my ANOVA stuff, and I'm once again pulling it in from a CSV file. You guys, once again, will have it from Excel. So this one, described by, just gives you the descriptive statistics of the data set that we were using. This is the Wendigo, Banshee, and Fae data sets, and number of human meals eaten. So this gives you just your descriptive statistics, a box plot of the data popping up over here. You don't have to make it super fancy or anything like that. X label creates the labels for the x-axis, Y label creates the labels for the y-axis, main creates the title over here. So pretty easy stuff. Levine's test probably isn't going to run for me. Nope, it does not run, because it never downloaded the package properly. But the t-apply is for your Shapiro-Wilks test, and it will also organize it for you for each group that you've run. remember, with assumptions, if it's significant, that's telling you that it's a problem and that it violates that assumption. I always see it as if it's significant, that's raising a flag to warn you that, hey, the Wendigo dataset isn't normal, but the Fae dataset is, but the Banshee dataset is not. So when you are writing your results and discussions, be sure to mention whether or not your assumptions were met or violated, but that you're going to continue to do the analysis because we told you to for this test. So the next portion, ANOVA analysis, user decision required. This is you actually running the ANOVA, and just for this activity, or I'm sorry, just for the test, I want you to run the one where the Levine's test was not significant, meaning you haven't violated the assumption, because half of you probably can't run the Levine's test anyway, and also it's required in order to be able to do the two keys as we've done it before. So that's important. So keep in mind that when running the ANOVA output, meals, which is my dependent variable, has come first, and group has come second. So when we run the summary, this is our output. We have an F value of 49.3 and a significant p-value. If we were to reverse these, run that, you get a warning message. Basically, R is like, hey, something's weird here. Things aren't okay. There's a problem. So make sure that your dependent variable goes first and your independent variable or your grouping variable goes second, for ANOVAs at least. So once again, just running that summary. Oops, I can't run the summary because I have erased the data. Click that, click that. So this is our ANOVA, and clicking here, we basically just get our means of each group. This is to just make sure that everything is where it's supposed to be in terms of your group size and your data size and stuff. You don't actually have to run this line of code. So moving on to the two keys. So the two key HSD, if you remember, we push it into took1. This is just a variable that we made up that conducts the test, but in order to actually see the results, we just have to, write took1 down here. And so it'll pop up, and these are your p-values, oops, these three here, to tell you your pairwise comparisons. So each of these is significantly different. So you would say that Fae is significantly different from Banshees, Wendigo is significantly different from Banshees, and Wendigo is significantly different from Fae in the number of human meals eaten, or whatever the context of your original dataset is. As far as effect size calculations, I'm going to talk to Tillman about it. I tried the code that he gave us in class when we were doing this, the effect size activity in class, and it did not work for me, and we didn't all go through it. So I'm not going to require you guys to do effect size for ANOVA. Yeah, so moving on. The regression portion is pretty easy. The library that you need is lntest. Once again, I'm using this, bringing in my own data, and I'm naming it regdata. I don't know if you guys have noticed, but like each one, in order to keep it organized, each one of my data frames, I've named something different. So mdata, tdata, vamp data, and now adding regdata. And that way I can just kind of keep track of what analysis I'm doing with what data set. You can nickname them whatever you want, or just use the full, what is that called? Full file name each time. But this is just what works for me. And honestly, I forgot to mention it because you guys will be importing your data sets, but whatever you import your data set as, you can just write the name of it out. So like if you say final Excel dataset is the name of your dataset from your computer, you can push it in to final. Oh darn, wrong side. Fin data, and have that as your variable, and then just fin data and whatever appropriate what are those things called? Whatever appropriate variables for the test that you're doing will pop up that way, just to make things easier for you. Sorry if I'm bouncing around a lot. I am doing this live and don't really have a script, so bear with me. So did regression data. So now we're doing output 1 is what we're naming our regression. And so the code is LM, reg data, math, and algebra. And when we do the summary, we get our non-significant p-value and our r squared, or I'm sorry, our adjusted r squared. So p-value is not significant, so I think for this one it was like math scores were predicting algebra grades. So there is not a significant prediction between math and algebra. And don't forget, actually should have done this first, but doing the Durbin-Watson test to make sure that your independence of residuals assumption has been met. And because this p-value is not significant, the assumption has been met, so we're cool here. Moving on to the last one that'll be expected to appear on the test are the chi-squared tests. So we have two kinds, the test of independence and the, what is the other one called? Test of independence and the goodness of fit. There we go. Can't remember for the life of me. So make this into C data, pulling that up, new variable. Make sure my library mass is up and active. And so for the chi-squared test of independence, we have TBL, and we're making the table based off of the store and the product type. So this was our, let's see if I can pull this up. So this was the stores and the product types. There were 3 options here, and I think 3 options here as well. And we wanted to see if there was a difference of if there was like more of one thing sold in one particular store, or if there was equal amounts sold across the stores. So when we run this, we create this, where'd it go? Table value. So in order to see what we ran, we have this table down here, and so everything kind of looks within the same range that, you know, they sell almost the same amount of things in each store. But when we run our actual chi-squared test, we get a non-significant p-value, so there is no difference in the, I think for the specific context of this problem, there is no difference in the type of item sold based off of the stores that they were selling them in. But it is very close to being significant, but doesn't matter because it did not reach that threshold of 0.05. So the next one, or I'm sorry, the final one is the goodness of fit. And for that one, I'm going to pull in a separate data set. And honestly, the pulling in the separate data set is just for me. You guys probably won't need to keep doing this portion for the test because it's all going to be the same data set, and in theory you could run it all at the same time, but we're not going to talk about that because that just gets too confusing. But I'm going to make the variable produced frequency, or yeah, prod frequency, doesn't matter, that can be anything. I could put blah 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 if I wanted to, and make a table of the data set with each of the employee names. So when I run this, I get a new table down here, and when I run this line, which is just this variable, it shows me each of the people with, I think for this one, how many days they took off. So Albert took 18 days off, Camila took 36 days off, Jimmy took 54 days off, and Susan took 12 days off. And for this problem, it was Jimmy thinks that he takes as many days off as everyone else, and that there is no difference. That's the null hypothesis. There should be equal days off taken among these 4 people. So for the next portion, prod probability, produce probability, and we're doing a data frame with C, and then remember, however many variables that you have, so we have 4, you have to make your expectancy table match that, and it has to add up to 1. So 25%, 25%, 25%, 25% is our expected frequency table. That would mean that, you know, everyone takes the same amount of days off. And if you want to, you can put 1 over 4 if that makes things easier. 1 over 4, 1 over 4, 1 over 4. And we run that, because it will read it the same way as 0.25. So if you were to have 3 groups, you would do 1 over 3, or 0.33, 0.33, 0.34, because it has to add up to 1. But that's just me talking. So we're going to run that, we ran that, and then do the chi-squared test of produced frequency, which is that first thing that we created, comma, p, which is saying it's the proportion, equals produced probability. So then we run that, and we get our significant p-value, which is telling us that there is a significant difference in the amount of days taken off by each employee. It doesn't tell us necessarily who's taking the most days off, it's only telling us that we expect it to be even. It's not even. So that's all. Hope this helps, and if you guys have any questions, feel free to text, call. I prefer not a call, I hate talking on the phone. Text, email, Slack, pop in at my office, any one of those things, and I'll be happy to help. Okay, bye.